1970. A strip mine in the American Midwest. The ground trembles as 46 tons of American steel bites into frozen shale that had defeated smaller dozers for months. Through clouds of diesel exhaust and flying rock, an Allis-Chalmers HD-41 pushes Earth like no machine ever built. 524 horsepower from a Cummins V12 turbo diesel, nearly 70 tons fully loaded. No competitor even came close. But engineering experts had been clear. No diesel engine yet built can sustain 500 horsepower under continuous heavy load. The metallurgy would fail. The cooling systems would overheat. The machine was too big, too expensive, too ambitious for real-world mining. Yet here it was, moving over burden that required blasting, running 12-hour shifts in sub-zero temperatures, doing what the experts said was impossible. 50 years later, these impossible dozers from strip mines still start, still push, still run, while modern dozers seize after 15,000 hours. The morning steam rose from coffee cups scattered across drafting tables in the Springfield plant as Jack Hammond spread the revised blueprints across the steel surface. The fluorescent lights hummed overhead, casting harsh shadows on the intricate mechanical drawings that would either vindicate his vision or destroy his career. Outside, the Illinois winter of 1968 pressed against the factory windows, but inside the engineering bay, the heat of ambition warmed the room. Hammond ran his calloused finger along the track frame specifications, tracing the 7-roller design that had kept him awake for weeks, 100 inches between track centers. 7.4 feet of gauge width, the numbers represented more than measurements, they were the foundation of American industrial audacity. Every European tractor manufacturer had settled on smaller frames, lighter construction, conservative power ratings. They built machines that lasted, certainly, but machines that whispered when the job demanded a roar. Bob Jenkins appeared at Hammond's shoulder, his foundry coveralls still bearing traces of molten steel from the night shift. The metallurgy specialist had been running stress calculations since dawn, his slide rule worn smooth from decades of calculating load tolerances. "Jack, the castings for those final drives are going to push our furnaces to their limits," Jenkins said, his voice carrying the weight of a man who understood that theoretical engineering meant nothing if the steel couldn't hold. Hammond nodded without looking up from the drawings. The planetary final drives represented the most critical component of the entire machine. Unlike conventional dozers that relied on simpler gear reduction systems, the HD-41 would demand planetary configurations capable of handling torque loads that had never been attempted in mobile earth-moving equipment. Each final drive housing would weigh over 800 pounds, cast from alloy steel specifications that Jenkins had spent months perfecting. The radiator placement had sparked the most heated debates in the engineering department. Traditional dozer design positioned cooling systems adjacent to the engine bay, but Hammond had insisted on relocating the entire cooling assembly behind the operator station. The decision defied conventional wisdom, but the mathematics supported his logic. A 524 horsepower Cummins VT17 10C diesel would generate heat levels that could overwhelm standard cooling configurations. By positioning radiators, hydraulic oil coolers, and transmission cooling systems at the rear of the machine, they could create a forced air cooling design that would push heated air away from the engine compartment rather than circulating it through the operator environment. Edward Masters entered the engineering bay carrying a manila folder thick with cost projections and maintenance estimates. His expression carried the skepticism that had become his trademark during the superdozer development process. "Jack, we need to discuss the hydraulic capacity requirements," Masters said, settling his reading glasses and opening the folder. 52 gallons of hydraulic oil in an open center system, 300 gallons of fuel capacity. The maintenance intervals alone will bankrupt smaller contractors. Hammond straightened, his eyes meeting Masters directly. The institutional doubter had raised valid concerns throughout the development process, but Hammond had learned to distinguish between legitimate engineering caution and reflexive resistance to innovation. "Edward, show me a mid-sized dozer that can move over burden without blasting. Show me a conventional machine that can operate 12-hour shifts in strip mine conditions without mechanical failure." The challenge hung in the air between them. Masters had witnessed decades of equipment failures, cost overruns, and broken promises from manufacturers who prioritized marketing over metallurgy. His caution stemmed from genuine concern for the operators who would depend on this machine in conditions that would destroy lesser equipment. But Hammond's confidence wasn't born from naive optimism. It emerged from systematic engineering analysis that had consumed 2 years of calculation, testing, and refinement. The transmission specifications represented another departure from industry standards. Twin Disc had agreed to manufacture a 3-speed power shift transmission designed specifically for the torque characteristics of the Cummins V12 diesel. The transmission would feature oil-cooled brake and clutch systems, planetary gear reduction, and torque conversion ratios that could translate the diesel's raw power into the mechanical advantage necessary for moving 46 tons of steel through rock and frozen earth. Jenkins returned to his calculations, measuring the 32-inch Grouser shoe specifications against ground pressure requirements. Single Grouser design with optional variants would provide the traction necessary for heavy ripping operations while distributing the machine's weight across a footprint that wouldn't sink into soft overburden. The track chains themselves would feature lifetime sealed construction, eliminating the maintenance requirements that had plagued earlier heavy equipment designs. Maria Sanchez arrived from the test site with mud still clinging to her steel-toed boots and diesel exhaust embedded in her work jacket. The field foreman's presence carried the authority of someone who had witnessed engineering promises fail under real-world conditions. "The prototype overheated yesterday after 12 hours of ripping," she reported, her voice cutting through the technical discussions with operational reality. "Transmission temperature spiked to 200 degrees. We had to shut down before we seized the torque converter." The room fell silent. Hammond felt the familiar knot of anxiety that accompanied every setback during the development process. They were building a machine that existed at the outer limits of current technology, pushing diesel engines, hydraulic systems, and metallurgy beyond proven parameters. Every failure validated the critics who insisted that American ambition had exceeded American capability. But Hammond had learned that innovation required persistence through failure. The transmission overheating confirmed his decision to relocate the cooling systems. The prototype had proven that conventional cooling placement couldn't handle the heat generated by sustained heavy-duty operation. The failure wasn't evidence of fundamental design flaws. It was confirmation that their revised cooling system represented the correct engineering approach. As winter darkness settled over the Springfield plant, Hammond remained at the drafting table, refining specifications that would either create the most powerful dozer ever built or destroy his reputation in American heavy equipment manufacturing. The stakes had never been higher, and the margin for error had never been smaller. The Cummins diesel roared to life in the pre-dawn darkness of a Minnesota iron range, its turbo diesel exhaust cutting white plumes through air that registered 15 degrees below zero. Maria Sanchez adjusted her hard hat and stepped closer to the machine that had traveled 800 miles from Springfield to prove itself in conditions that had defeated conventional dozers for decades. The HD-41 sat like a steel monument against the frozen landscape, its 46 tons of American engineering ready to challenge everything the mining industry believed about heavy earth moving. Jack Hammond watched from the elevated observation platform as Sanchez climbed into the operator's compartment, her movements deliberate despite the bulky winter clothing that mining operations demanded. 6 months had passed since the prototype trials at Springfield, 6 months of metallurgical refinements, cooling system modifications, and hydraulic adjustments that had transformed Hammond's theoretical calculations into operational reality. The machine before them represented the culmination of engineering decisions that had pushed American heavy equipment manufacturing beyond conventional limits. The test site stretched across 12 acres of overburden that contained everything nature could devise to destroy mechanical equipment. Frozen shale embedded with granite boulders, clay deposits that had hardened into concrete-like consistency, rock formations that would require blasting with conventional mining methods, The Minnesota Mining and Manufacturing Company had agreed to provide the testing ground with the understanding that if the HD-41 could operate effectively in these conditions, it could operate anywhere in North America. Sanchez engaged the hydraulics, and the massive blade dropped into contact with the frozen earth. The Cummins V12 responded immediately, its 524 horsepower translating through the twin-disc transmission into mechanical force that began moving material conventional dozers couldn't scratch. The 7-roller track system distributed the machine's weight across the 32-inch Grouser shoes, preventing the sinking and slipping that had plagued lighter equipment in similar conditions. Edward Masters stood beside Hammond on the observation platform, his skepticism evident despite the impressive initial performance. 12 hours, Jack, Masters said, his breath forming ice crystals in the frigid air. If she can run 12 hours in this cold without mechanical failure, I'll admit your engineering might have merit. The institutional doubter had witnessed too many promising prototypes fail when subjected to sustained operational stress to celebrate preliminary success. The morning progressed with methodical efficiency. Sanchez operated the HD-41 through a series of tests designed to evaluate every system under maximum load conditions, ripping operations that would normally require pre-blasting, pushing loads that exceeded the capacity of 3 conventional dozers working in tandem, maneuverability tests that demonstrated the machine's ability to operate in confined spaces despite its massive dimensions. Bob Jenkins monitored the hydraulic and cooling system performance from his mobile testing station, recording temperatures, pressures, and operational parameters every 15 minutes. The relocating cooling system design was performing exactly as Hammond had calculated. Radiator temperatures remained stable despite the engine's sustained high output. Hydraulic oil maintained optimal viscosity despite the sub-zero ambient conditions. The transmission cooling system prevented the overheating that had plagued earlier prototypes. By midday, the HD-41 had moved more overburden than the mining company's 3 conventional dozers had, moved in the previous week. The elimination of blasting requirements alone represented cost savings that exceeded 20% per cubic yard of material moved. The machine's ability to bite through frozen shale and push granite boulders without mechanical stress demonstrated capabilities that mining engineers had considered impossible with mobile earth-moving equipment. The afternoon brought the most challenging test conditions. Temperature dropped to 22 degrees below zero. Wind gusts created visibility problems that would have halted conventional operations. The overburden contained rock formations that had broken cutting edges on previous equipment. Sanchez continued operating the HD-41 with mechanical precision, the machine's performance unwavering despite conditions that exceeded the operational parameters of any existing dozer. At 4:30 in the afternoon, with darkness approaching and the test schedule calling for shutdown, Sanchez radioed from the operator's compartment. "Jack, she's still hungry for Earth. Engine temperature stable, hydraulics responsive, tracks holding perfect. This machine wants to keep working." Hammond felt the vindication that accompanied successful innovation. The HD-41 wasn't simply meeting performance expectations. It was exceeding them by margins that would revolutionize surface mining operations. The systematic engineering approach that had guided every design decision was proving itself under real-world conditions that represented the most demanding operational environment in North American mining. The final test came at sunset when Sanchez encountered a section of overburden that contained shale formations embedded with iron ore deposits. The material had defeated conventional equipment through a combination of hardness and abrasive characteristics that destroyed cutting edges and overwhelmed hydraulic systems. The HD-41 approached the formation with mechanical confidence, its blade engaging the rock with force that transmitted through the track system into the frozen ground. The shale began to fracture. The iron ore deposits yielded to mechanical pressure that conventional dozers couldn't generate. The HD-41 pushed through material that had required explosives for removal, demonstrating operational capabilities that mining engineers had insisted were impossible with mobile equipment. As the Minnesota test concluded after 14 hours of continuous operation, Hammond knew they had created more than a powerful dozer. They had built a machine that would redefine American mining operations, eliminate operational limitations that had constrained surface mining for decades. and prove that systematic engineering could overcome conventional wisdom about mechanical limitations. The HD-41 sat silent in the Minnesota darkness, its steel surfaces radiating heat from sustained operation that had pushed every system beyond proven limits without failure. Steam rose from the cooling systems, testament to the engineering precision that had made sustained heavy-duty performance possible in conditions that would have destroyed conventional equipment. The first catastrophic failure occurred on a Tuesday morning in March of 1971 at a limestone quarry outside Louisville, Kentucky. Jack Hammond received the telephone call at 7:15, the voice of the quarry superintendent crackling through long-distance static with news that would threaten everything they had built. "Your machine just lost its right final drive. Planetary gears are scattered across 50 yards of quarry floor, oil everywhere. The operator's shaken but unhurt." Hammond set down the receiver and stared across the Springfield engineering bay where Bob Jenkins was reviewing metallurgical reports from the previous month's production run. The HD-41 program had delivered 12 machines to mining operations across the Midwest, each one performing beyond initial expectations, each one representing millions of dollars in development costs that Allis-Chalmers had invested in Hammond's vision of American heavy equipment supremacy. Within 48 hours, 2 more failures arrived by telephone. A quarry in Pennsylvania reported planetary gear housing cracks that had allowed lubricating oil to drain during a ripping operation, causing the entire final drive assembly to seize under load. An iron mine in Michigan experienced seal failures that contaminated the gear oil with rock dust and water, leading to complete mechanical breakdown after 6 hours of operation. Jenkins arrived at the Springfield plant before dawn, his usually methodical demeanor replaced by the urgency that accompanied engineering crisis. He had driven through the night from the Kentucky quarry, where he had spent 16 hours examining the failed components with the precision of a medical examiner conducting an autopsy. The evidence painted a disturbing picture of metallurgical limitations that threatened to invalidate 2 years of development work. "The planetary gear housings are cracking under sustained torque seal loads," Jenkins reported, spreading photographs of the failed components across Hammond's drafting table. "The alloy specifications we developed can handle intermittent stress, but continuous rock ripping generates harmonic vibrations that create fatigue cracks in the casting. The cracks allow oil pressure to escape, which leads to lubrication failure and complete mechanical destruction." Edward Masters entered the engineering bay carrying a manila folder containing cost projections and customer communications that represented the business consequences of mechanical failure. His expression carried the grim satisfaction of someone whose cautions had proven prophetic. "The Louisville quarry is threatening to cancel their order for 6 additional machines. They're citing unsafe design and demanding immediate removal of the failed unit. Legal is concerned about liability exposure if operators are injured." Hammond studied the photographs of destroyed planetary gears, each twisted piece of steel representing a fundamental challenge to the engineering principles that had guided the HD-41 development. The failures weren't random mechanical breakdowns. They revealed systematic design limitations that conventional wisdom had predicted. The planetary gear assemblies that enabled the machine's incredible power transmission were failing precisely where critics had insisted they would fail. Maria Sanchez arrived from the Pennsylvania quarry with first-hand testimony that confirmed Hammond's worst fears. The machine was ripping through limestone formations, running smooth as silk, when the right final drive started making noise like grinding metal. Operator tried to back out, but the planetary assembly locked up solid. When the drive seized, the blade was still engaged in the rock formation, and the hydraulic load shifted to the left track. The whole machine twisted sideways and jammed against the quarry wall. The description painted a scenario that revealed the cascading consequences of final drive failure during heavy ripping operations. When one drive assembly seized, the machine's massive momentum and the resistance of embedded rock created mechanical forces that the frame wasn't designed to absorb. The resulting structural stress had bent the main frame rails and cracked mounting brackets that supported the hydraulic system. Bob Jenkins had spent the previous week conducting failure analysis that revealed the fundamental metallurgical challenge they faced. "The continuous rock ripping generates torsional stress that exceeds our original calculations," he explained, pointing to stress analysis charts that documented the mechanical forces involved. When the machine encounters buried boulders or dense rock formations, the planetary gears experience shock loads that can reach 8,000 foot-pounds of torque. Our current housing design can't absorb that level of sustained punishment. The financial implications became clear when Masters presented the cost analysis for addressing the final drive failures. Redesigning the planetary gear housings would require new casting patterns, upgraded alloy specifications, and extensive testing that could consume 6 months and $2 million. Customer confidence had evaporated with each mechanical failure, and orders for additional machines had stopped completely. Hammond found himself defending the super dozer concept against criticism from within Allis-Chalmers management and from the mining industry that had initially embraced the HD-41's capabilities. "We overreached," became the refrain from company executives who had supported the program, when success seemed assured but were now calculating the costs of failure. "Go back to mid-sized tractors. Build machines we understand." The psychological impact on the Springfield plant workforce was immediate and devastating. Union workers who had taken pride in building the most powerful dozer ever manufactured began questioning whether American ingenuity had exceeded American capability. The foundry workers who cast the failed components felt personal responsibility for the mechanical breakdowns that threatened jobs and the plant's reputation. For 3 weeks in April of 1971, the HD-41 program existed in limbo while Allis-Chalmers management debated whether to invest additional resources in solving the final drive problem or abandon the superdozer concept entirely. Hammond spent sleepless nights reviewing metallurgical specifications and planetary gear designs, searching for engineering solutions that could salvage 2 years of development work and vindicate his vision of American heavy equipment leadership. The program's survival hung on a decision that would determine whether systematic engineering could overcome the mechanical limitations that had destroyed conventional wisdom about dozer capabilities. The redesign began in the pre-dawn darkness of May 1971, when Jack Hammond arrived at the Springfield plant carrying blueprints that represented either salvation or the final collapse of American heavy equipment ambition. Bob Jenkins had spent 3 weeks calculating metallurgical specifications that would address every failure mode identified in the planetary gear housing catastrophes, and his conclusions demanded engineering changes that would test the limits of American foundry capability. Hammond spread the revised drawings across the drafting table, where the original HD-41 had been conceived 2 years earlier. The new final drive housings would require casting patterns 30% larger than the original design, with wall thicknesses increased from 3/4 of an inch to 1 1/4 inches at critical stress points. The alloy specification called for steel compositions that contained higher concentrations of molybdenum and chromium, creating metallurgical properties that could absorb the torsional shock loads generated during sustained rock-ripping operations. Jenkins examined the casting requirements with the methodical precision that had earned his reputation as one of the Midwest's most capable metallurgy specialists. "The new housings will weigh 1,200 pounds each," he reported, his slide rule calculations confirming the weight increases that would ripple through every aspect of the machine's design. "We'll need to upgrade the mounting brackets, strengthen the frame rails, and increase the hydraulic system capacity to handle the additional mass." The hydraulic system modifications represented the most complex engineering challenge. The original open-center hydraulic design had provided 52 gallons of oil capacity, sufficient for the initial planetary gear specifications, but inadequate for the upgraded final drives that would operate under continuous high-pressure conditions. Hammond calculated that the new system would require 78 gallons of hydraulic oil, with pressure ratings increased from 1,800 to 2,200 pounds per square inch. Edward Masters entered the engineering bay, carrying procurement estimates that quantified the financial stakes of the redesign effort. "The new casting patterns will cost $400,000. The upgraded alloy specifications will increase material costs by 40% per machine. We're looking at 18 months of development time and $3 million in additional investment before we can deliver a single upgraded unit." Hammond understood that the company's patience had been exhausted by the initial failures. Management had authorized the redesign with the explicit understanding that no further mechanical breakdowns would be tolerated. The HD-41 program had one opportunity to prove that American engineering could overcome the limitations that had defeated the original design. The foundry modifications began in June with the installation of upgraded furnaces capable of achieving the higher temperatures required for the new alloy specifications. Jenkins supervised the construction of casting patterns that incorporated cooling channels designed to eliminate the internal stress concentrations that had created fatigue cracks in the original housings. Each casting would require 16 hours of controlled cooling under conditions that demanded absolute precision in temperature management. Maria Sanchez arrived from the field testing sites with operational data that would guide the hydraulic system improvements. The original machines generated hydraulic pressures that spiked to 2,400 pounds per square inch during maximum ripping operations, she reported, her field notes documenting the pressure surges that had stressed seals and contributed to oil contamination. The new system needs redundant pressure relief valves and larger oil sumps to handle sustained high-pressure operation. The track system modifications focused on distributing the additional weight represented by the upgraded final drives and strengthened frame construction. The 7-roller undercarriage design remained unchanged, but the track shoes were reinforced with additional steel thickness that increased their individual weight from 120 to 145 pounds. The track chains received upgraded pins and bushings designed to handle the increased mechanical loads, without compromising the lifetime seal construction that eliminated maintenance requirements. By September of 1973, the first prototype of what would become the HD-41B had been assembled at Springfield with mechanical specifications that addressed every failure mode identified in the original design. The machine weighed 52 tons compared to the 46-ton weight of the original. HD-41, with the additional 6 tons distributed across final drive assemblies, frame reinforcements, and hydraulic system components that would enable sustained operation under conditions that had destroyed the earlier machines. The field testing began at the same Minnesota Iron Range where the original HD-41 had proven its basic capabilities 2 years earlier. Sanchez operated the upgraded machine through test conditions designed to replicate the rock formations and sustained loading that had caused the planetary gear failures. The new final drive assemblies absorbed shock loads that would have destroyed the original components, their upgraded metallurgy and increased oil capacity maintaining operational integrity under stress levels that exceeded the most demanding mining conditions. Hammond monitored the testing from the observation platform, recording operational parameters that documented the engineering triumph his systematic approach had achieved. Hydraulic pressures remained stable under maximum load conditions. Final drive temperatures stayed within acceptable ranges despite continuous rock ripping operations. The cooling system maintained optimal performance during 12-hour operational cycles that would have overwhelmed conventional dozer designs. The first production HD-41B machines were delivered to mining customers in early 1974, each one representing the culmination of engineering refinements that had transformed initial failure into mechanical supremacy. The quarry operations that had experienced catastrophic breakdowns with the original machines reported operational reliability that exceeded 90% uptime during sustained production cycles. Cost per cubic yard calculations showed efficiency improvements that eliminated blasting requirements and reduced operational expenses by 25% compared to conventional dozer operations. Bob Jenkins stood in the Springfield foundry, watching molten steel flow into casting patterns that would produce final drive housings capable of withstanding mechanical forces that had seemed impossible 3 years earlier. The upgraded metallurgy represented more than engineering refinement. It embodied the systematic persistence that distinguished American innovation from conventional mechanical design. The HD-41B had proven that methodical engineering could overcome any limitation, that American ingenuity supported by systematic analysis could achieve mechanical capabilities that defied expert prediction. 43 years after the first HD-41 rolled off the Springfield production line, Jimmy Crawford discovered what remained of American heavy equipment supremacy rusting beneath kudzu vines in rural Allendale County, South Carolina. The 1972 HD-41B sat where it had been abandoned in 1998, its steel surfaces oxidized but structurally intact, its Cummins V12 diesel still mounted in the engine bay that had been designed to last generations rather than fiscal quarters. Crawford had built his reputation restoring vintage construction equipment for collectors and equipment shows across the Southeast. He understood the difference between machines built for durability and machines built for profit margins. The HD-41 represented engineering philosophy that prioritized mechanical longevity over manufacturing efficiency, systematic strength over contemporary convenience. The restoration process revealed the fundamental differences between 1970s American heavy equipment design and the computerized dozers that had replaced them in modern mining operations. Crawford drained hydraulic oil that had maintained its viscosity despite 16 years of exposure to South Carolina humidity. He disassembled final drive assemblies that showed minimal wear despite operational histories that exceeded 30,000 hours of strip mine service before retirement. The track system components demonstrated metallurgical properties that modern manufacturers had abandoned in pursuit of lighter construction and reduced material costs. The 7-roller undercarriage frames showed no structural fatigue despite decades of supporting 52 tons of machine weight. The lifetime sealed track chains retained their original lubrication, their pins and bushings exhibiting wear patterns that suggested another 20,000 hours of operational capability. Bob Jenkins, now 78 and officially retired from foundry work, visited Crawford's restoration shop during the engine rebuild process. The metallurgy specialist examined the cylinder heads and engine block with the same methodical precision he had applied to the original casting specifications 4 decades earlier. The Cummins V12 was built when diesel engines were designed to run forever, Jenkins observed, running his experienced fingers along cylinder walls that showed minimal scoring despite the engine's operational history. Modern engines are computer-controlled, fuel-efficient, emission-compliant, and they fail after 15,000 hours because they're built to be replaced, not rebuilt. The hydraulic system restoration provided the most dramatic evidence of the engineering philosophy that had guided the HD-41 development. Crawford disassembled hydraulic cylinders that retained their original seals and showed no internal corrosion despite years of exposure to moisture and temperature variations. The open-center hydraulic design had eliminated the complex electronic controls and precision machine components that made modern dozer hydraulic systems vulnerable to contamination and electronic failure. Maria Sanchez arrived at the restoration shop carrying operational logs from HD-41 machines that remained in service at aggregate quarries across the Midwest. At 71, the former field foreman had transitioned to equipment consulting, helping mining operations maximize productivity from aging equipment that modern manufacturers no longer supported. I've got 3 HD-41s still running production shifts at quarries in Illinois and Indiana, she reported, her field notes documenting operational reliability that exceeded anything achieved by contemporary equipment. Average operational hours on those machines is 42,000. They're still moving more overburden per shift than modern dozers, costing 3 times as much. The contrast with modern dozer reliability had become a source of industry frustration for mining operations that had invested millions in computerized equipment, promising improved efficiency and reduced maintenance requirements. Crawford's restoration work brought him into contact with quarry operators who described contemporary dozer failures that had become routine operational expenses. Transmission control modules that failed after exposure to dust and vibration. Hydraulic systems that required complete replacement when electronic sensors malfunctioned. Track frames manufactured from lighter alloys that developed stress cracks after 8,000 operational hours. The completed restoration of the Allendale County HD-41B attracted attention from equipment collectors and mining industry veterans who recognized the machine as representative of American manufacturing capability that had been sacrificed for quarterly profit targets and international cost competition. The diesel engine fired immediately, despite having sat dormant for 16 years. The hydraulic systems achieved full operational pressure without leakage or performance degradation. The machine moved under its own power with mechanical authority that modern equipment couldn't replicate. Jack Hammond attended the equipment show debut of the restored HD-41B at age 84, his presence drawing crowds of industry veterans who remembered when American heavy equipment led global mining operations through systematic engineering rather than marketing sophistication. Hammond approached the machine with the deliberate steps of advanced age, but the alert eyes of an engineer whose theoretical calculations had been vindicated by decades of operational proof. He placed his weathered hand on the blade that had been designed to move mountains, feeling the cold steel that had outlasted the careers of operators who had retired, companies that had been sold, and industries that had been transformed by global economic forces. The HD-41 represented more than successful engineering. It embodied the systematic American approach to mechanical problem solving that prioritized functional durability over contemporary fashion. "We didn't build a dozer," Hammond said to the crowd of equipment enthusiasts and industry professionals who had gathered to witness the restoration. "We built a legacy that proves American ingenuity endures when engineers design for purpose rather than profit." The restored HD-41B sat gleaming under the exhibition tent, its steel surfaces reflecting 40 years of operational history that had proven systematic engineering could create mechanical capabilities that transcended the limitations of conventional wisdom. When engineers build with purpose, strength, and simplicity rather than chasing speed or fashion, American innovation creates machines that outlast the companies that built them and the industries they were designed to serve.